Okay, welcome back. So today I would like to discuss how do you use functions to solve counting problems. As we have said, the classical probability has a lot to do with counting, and so it's important to find smart ways of counting. Okay, so this is a subject which is a very beautiful subject and is dealt with in a field which is called algebraic combinatorics, and in the lecture notes you will find a reference to a book which can also be found online by Philippe Flageolet. That is a lot more detail. I will just scratch the surface and give you the main idea. Okay, so what is the problem? So imagine that you have a class of objects and these objects, let's call them A. These are the elements of this class, and each of these objects has a size which is an integer. Okay, and the question, the main question that we want to address is how many objects of size n are in the class A. So how many objects of size n does A contains? So for example, you may think of objects as being graphs of a certain type. So a graph is a set of nodes with links. Okay, and you may want to compute, you may want the size. So this is a particular object, and you may be interested in the class of all possible, the class of all possible graphs that you can build, and the size of this graph is equal to the number of nodes. Okay, and then the question you want to ask is how many graphs of n nodes can I build? Okay, so now the main tool that we will use is what is called the generating function. And given a certain class of objects, we define it as the function A of S, which is equal to the sum of all objects in this class of Z raised to the power the size of object A. Okay, so the main idea is that now if you rearrange this sum and group all objects of size n, then this generating function, so this is S, this generating function will be of the form an times s to the n, and this number an is exactly the answer to this question. It's exactly the number of objects of size n. Okay, So if you are able, by the definition of what this class is, to write down an equation for the generating function, and then you can look at its power expansion, then you can read, compute the coefficients of s to the n, and this will give you the number of objects of size n. Okay, so there are operations that you can do on the sets, and these the operation that you can do on the sets then translate into operations that you can do on the generating functions, or operations that you can do on the number of objects of a certain size, on this sequence. Okay, so the first operation that we are going to consider is the sum, or the union, and this means that so when we are interested in a class of objects that is the union of two different classes of objects, when these class of objects do not intersect. So this means that we are interested in objects which are either of type A or of type B. Okay? Then for objects of, in this class C, we can build its generating function. Sorry, this is, I define it as S. So this is the sum of all objects in class C of S to the power of size of C. Now, what is the size of C? Well, this sum, I can split it as either a sum, so C is either in A or in B, so I can split this sum as on objects in A of S to the size A, or sum of objects in B of S to the B. Okay, because this sum runs on all objects either in A or in B. Okay, and this means that the generating function of a union of sets is just the sum of the generating functions. Okay, where this is equal to this, and this is equal to this. Okay? Very good. So the next example that we can consider is the product. Okay, so what does this mean for the coefficients? Well, it means that the number of objects of size n in C is equal to the number of objects of size n in A plus the number of objects of size n in B. Okay, so this is intuitive. Okay. So the next operation that I'm going to consider is the product. Okay, so here I'm going to consider a class of objects that are composed of two parts. So each object in C is a pair of an object in A and an object in B. Okay? Where A belongs to A and B belongs to B. Okay, then if I compute the generating function of Z of C, then this is the sum on all objects in C of S to the power of C, a sum over all the objects in this class, S to the power of this. But here, the size of an object of this type is the sum of the sizes of the objects in A and in B. Okay, so this is the sum over C of S to the A plus S to the B, that I can write as S to the B. Okay? At the same time, also this sum, I can write it as a sum over all the A, or all the objects in A, and a sum over all the objects in B. Okay, so you can see that I can factorize this sum times S to the A, this sum times S to the B. So what I get is the product of the generating functions. Okay, so you see that union and sum and product of sets translate into sum and products of the generating functions. Okay, so let me do a simple an example of this. Actually, this is a problem that interested Euler for some time, and for which he gave the solution. So this is a problem of triangulations. Of polygons. So what is the problem? So if you have a polygon, sorry, say something like this, then and let's say a polygon, let's say there are n plus 2 edges. Okay, because a polygon with 2 edges would be just something like this, so it's not really a polygon. So you start from n, so from polygons with 3 edges. So you can divide these polygons into triangles, like for example in this way. Okay, so here there are 1, 2, 3, 4 triangles. But you can do this in many ways. So this is one way. So this would be another way, etc., etc. Okay. So the question is in how each of these is a triangulation. And the question is, if you have a polygon n plus 2 edges, how many triangulations does it admits? Okay. So the idea that we shall consider is that we consider the set T of triangulations. So each element of this set is a possible triangulation of a polygon. Okay? And now, for every triangulation, for this set of triangulation, we can observe that any triangulation can be obtained if I say remove one edge, let's say I remove this edge here, so I have this polygon here, and this polygon here. Okay, I have removed this edge. Okay, so each triangulation, such as for example this one, okay, can be represented as the number of, as a triangulation of smaller polygons of, let's say, m plus 2 edges times plus a triangle plus a triangulation of a polygon of n minus m plus 1 edges. Okay? So you can check in this case n is equal to 4, this m is equal to 1, this has 3 edges, and this is 4 minus 1 plus 1 is 4 edges. Okay? Very good. So what does it mean? So it means that the set of triangulations is first of all, you have the empty set, which is the triangulation of the set with n equal to 0, that we include in this set. And then, so either it is the empty triangulation, or it is a triangulation that is formed by a triangulation times one single triangle times a triangulation. Okay? So any triangulation is, so the set of triangulation is the set of triangulation of a smaller polygon plus a triangle plus another times another set of triangulation. Okay, so this, if you use these two relations there, this tells you that the generating function of triangulations is equal to the generating function of this plus the generating function of this. The generating function of the empty set is just a set with 0 elements, so with elements of size 0, so it's just 1, plus the generating function of this. Now, the generating function of this is the generating function of this times the generating function of this times the generating function of this. So this is T of Z, the generating function of a set with a single triangle. So this is a set with just one element of size 1. So it's just, sorry, I should use S. It's just S times T of S, which is the generating function of T. Okay, so you see that here you get a quadratic equation for T, so that you can solve, and if you solve this quadratic equation, you get 1 minus square root of 1 minus 4s divided by 2s. Okay? And now, actually, it's a quadratic equation, so you get both signs, but here you should choose one of the two signs, and the way to choose one of the two signs is to observe that you want the T of 0 to be T of 0 is equal to the number of triangulations of size 0 that you have, which should be equal to 1. Okay? So, and also from this equation you see that T of 0 is equal to 1 if S is equal to 0. Okay? So essentially You see that if you take the plus sign, this diverges, so you have to take the minus sign, and so with the minus sign, this is okay. So now we can use the binomial expansion and write this as 1 over 2s times 1 minus the sum over n from 0 to infinity. Here you have 1/2 choose n times minus 4 s to the power n. Okay. So this this expression is a little bit complicated, but if you work a little bit and rewrite this as we have done in previous lecture for minus 1/2 choose n, then what you find is that you can write this in a simpler form as sum from n equal to 0 to infinity of a constant times s to the n, where this Cn is given by 1 over n plus 1, 2n choose n, and this is a famous sequence because these are called Catalan numbers. Okay, so you see, with the use of generating function and understanding what is the relation, the defining relation of this set, so this equation defines what is a triangulation, then you can write down an equation for the generating function, and you can compute the number of triangulations of a polygon of n plus 2 edges. Okay? Okay, so there are more complicated, there are more complex operations that you can do on these sets in order to solve more complex or more problems. And I will just discuss another very useful operations that you can do on this set, which is the sequence. Okay. Okay, so so the sequence. So if you have a set A, in many cases you are interested in objects which are a sequence of objects taken from a different set. Okay, so well, these AI are in some set A, and then you are interested in objects C, which are a sequence of objects taken from this A. Say, for example, if you, so an example is an integer. So you can write an integer as a sequence of dots, okay, where there are n dots. Okay, so in this case, your set A is just the set of with just one dot. Okay, and an integer is just a sequence of dots. Okay. Now, so the set C that you are interested in is just either the empty set that we considered, or the set A. This contains all sequences of length 1, or the set A times A. This contains all sequences of length 2, etc., etc. Okay, then you have the sequences of length 3, etc., etc. Okay, Now, then the generating function of the set C of sequences, so we write this as a sequence of A. So the generating function of the set of sequences can be computed from this, because this is just the sum of the generating function of this plus this plus this. So the generating function of this is 1, the generating function of this is A of S, this one as generating function A of S squared, etc. You have all a power expansion, a sum of all powers of the generating function A. So, and you can sum this in a geometric series, and this gives you 1 divided by 1 minus A of S. Okay, so for example, if you want to compute the generating function of integers, well, this is very simple, so is 1 divided by 1 minus the generating function of this set here, but this is just one element of size 1, so this is just S, okay? And indeed, when you expand this, this is 1 plus S squared plus, so all coefficients are equal to 1, which means that there is only one integer of size n. So if you consider, for example, a more complex situation, so for example, binary words, then binary words are sequences of zeros and ones, okay, sequences of zeros and ones. So the set A, in this case, is a set of 2 elements, okay? So the generating function of the set of binary words, let's call it B of S, then is 1 divided by 1 minus 2 times S this time, because the generating function of this set is 2 times S, because there are 2 objects of size 1. Okay, and then this is just the sum n 0 to infinity, 2 to the n times S to the n. This tells you that there are 2 to the n binary words of size n, which is actually intuitively true. Okay, so let me make an example which is a little bit more complicated, which is the one of rooted plane trees. So what is a rooted plane tree? So a rooted plane tree is a tree that starts from a root, and then it branches to other nodes, etc., etc. Okay. So so the idea, so this is a tree in the sense that there are no, it's a graph without loops, and it's rooted because there is it starts from a root, and its plane means that the subtrees that emanate from each node are ordered. So this tree, for example, is a different tree from the one where you just exchange this part with this part, okay? Because the order of these sub-trees will change, okay? So, exactly, by the way, so if you set T to be the set of all rooted plane trees, then what we can say? Well, we can say that this set, so every rooted tree is essentially a node times when you remove this node, what you have here is a sequence of trees. So every tree is composed of essentially a root node plus a sequence of subtrees, okay, which are these ones. Okay. So this is the defining equation for rooted plane trees, and it translates immediately into an equation for the generating function. So the generating function of T is equal to the generating function of this, which is just S, times the generating function of the sequence of T, which is 1 minus T of S. Okay, so, and these again, if you multiply this on this side, again you get a quadratic function for T of S. And this quadratic function, you can solve it, and it has a solution which is, again, there are two roots, but you have to choose the right one, which is given by this, okay? So you realize that this expression is very similar to the one that we have obtained before for the triangulations. So indeed, when you work out the power expansion of this expression, what you find that this is given by Catalan number of order n minus 1. Okay, so this tells you that the number of rooted plane trees of n nodes is equal to the number of ways you can triangulate a polygon of n plus 1 sides. Okay, so again, this is Catalan number. Okay, so there are even more complicated constructions that you can consider, and these are discussed in the lecture notes, such as power set and a multi-set. And these are important for problems that relates to integer partitions and integer compositions, which is a very interesting branch of number theory. But I will not go into these details, because these are essentially all the operations that we will consider. So the only thing I want to mention again is what happens when here what we have considered is objects where the different components are not labeled. Okay, so for example, you can consider a tree like, say, for example, this one, and but you can also consider this tree when the nodes are labeled, say by 1, 2, 3, 4, 5. Okay, and you see that for an object of size n, there are n factorial ways of labeling it. So if we want to consider labeled objects, we want to compute labeled objects, then you should take this into account. And this is why, say, for labeled objects, the generating function that one considers are slightly different. And they consider they are built in this way. Okay, so or if you want sum of the objects A of S to the A divided by A factorial, and this these accounts exactly for the for this sorry, no. So the generating function is defined in the same way, okay, but if you yeah, no, sorry. If you define the generating function in this way, then what one can see is that the generating function satisfies the same properties that we have seen. Say, for example, consider the situation where we consider the product objects that are composed of two parts. Okay, so if I have an object, if I want to count the number of objects, labeled objects of size n, then I have to compute, of course, I have to sum on all objects of size k from 0 to n of set A. And so this would be, if these are the number of objects of type A of size k, which are labeled, then this is the number of objects of size n minus k of type B, labeled objects of. Then I have to compute these two things, but then I have to add a combinatorial factor that tells you if I take k objects of size k objects in A and n minus k objects in B, in how many ways can I relabel the composite objects of size n? Okay, and so you see that then Cn divided by n factorial is equal to sum over k from 0 to infinity of ak over k factorial b n minus k over n minus k factorial, which means that again if I multiply by s to the n and sum over n, then again for this operation I will get that the generating function, when it is defined in this way, satisfy the product rule. Okay. So it is interesting to notice that the same generating function describes both, may describe both labeled and unlabeled objects. So the simplest example is we discussed integers. So we said that the integers are just the sequence of this set. Now, if I consider instead labeled objects, so I can consider the permutation as a sequence of objects that have a label. Okay, every object has a different label. Okay, and then you see these two. So the generating function for these we said is just 1 minus s. But for these also you can say that a permutation is just an element of size it's just the sequence of a set of one object. So the generating function would be exactly the same. Okay, and indeed, if you consider this as the generating function of labeled objects, then you have to write it in this way, and so you see that the number of permutation now, because because this generating function is just sum of n from 0 to infinity of s to the n, the coefficient is 1, then the number of permutations must be equal to n factorial. Okay? So, very good.